Hi there, welcome to this video where we're going to take a look at some of the contents of Whitehead and Russell's Principia Mathematica. As usual, it's the first edition that we're going to be taking a look at in this video, and in particular we're going to be looking at volumes 1 and 2 in this video. So this is the third video on Principia Mathematica that I've uploaded over the last, I don't know, maybe week or so. So the reason that I'm uploading so many videos is because I've got quite a lot that I want to say about Principia Mathematica. I don't know how long I'm going to be able to keep this up for, but really as long as I've got anything to say. So as with the last couple of videos that I've uploaded, this video is fairly, in fact, this is unscripted. This video is completely unscripted. I don't even have notes to refer to with this video. So all I've got is a basic plan of what I intend to talk about in this video. So if I do kind of stumble over my words sometimes, and if I do kind of repeat myself a little bit, then that's because I'm deciding what I want to say and how I want to say it as I'm actually saying it. So you'll just have to bear with me on that one. So a lot of my previous videos have been fairly well planned and put together and everything, but that's not the case for this video. So what we're going to be looking at in this video is something actually that I touched on in the last video that I made. Right at the end of my last video, I started to ramble on a little bit about arithmetical class sums and things like this. Actually, I want to continue. I want to go into more detail with that. So in this video, I want to have a look at how in Principia Mathematica is addition of cardinal numbers defined, or maybe I should be a bit more specific. How do we add two cardinal numbers together, which can naturally be extended to any finite number of cardinal numbers? But there is a more general case of addition of cardinal numbers which doesn't distinguish between finite sums and infinite sums and things like that. So I'm not going for the general case. I'm just going for the case where we're adding two cardinal numbers together. Now, there's all sorts of issues with this that we're going to look at in this video. One of the consequences, by the way, of cardinal addition is that we will find that 1 plus 1 is equal to 2. So if you watch some other videos on YouTube, maybe that talk about Principia Mathematica, that mention Principia Mathematica, as well as all of the padding about, general biographical details about Whitehead and Russell, what's likely to come up at some point is that, Whitehead and Russell took 700 odd pages to prove that 1 plus 1 equals 2. And this is usually presented as if it's some kind of big result in Principia Mathematica. Like this was the centerpiece of Principia Mathematica, what the authors were aiming for. And so that's not the case at all. 1 plus 1 equals 2. We'll see that in this video, that 1 plus 1 is equal to 2. But really, it's just a corollary from many of the results that have gone before, much more general results that have gone before. If Whitehead and Russell really wanted to prove that 1 plus 1 equals 2, they needn't have gone to the trouble of Principia Mathematica. To prove that 1 plus 1 is equal to 2 is very straightforward. 1, 1, 2. Very straightforward. But the reason why Whitehead and Russell took so long to prove that 1 plus 1 equals 2 is because of the starting point and what the general aim of the authors were. So the aim of the authors was to find, or to form a purely logical, theoretical foundation for mathematics. So starting from the most simple and basic logical principles, developing these into the complex mathematical system that we typically intuitively understand. Okay, and this is a lot of work. So you don't start out with a concept of number. A number, a cardinal number in Principia Mathematica is a very complicated structure. They're very complicated complex entities. So it's hardly surprising, really, that they took as long as they did to prove that 1 + 1 = 2. But it certainly wasn't one of their main aims to prove that 1 + 1 = 2. Now, there's some things that we're going to have to bear in mind in this video. We're going to have to keep in mind what Whitehead and Russell, one of Whitehead and Russell's aims was maximum generality, really, in whatever sense they understood that term. So I'm not going to try to define what I mean by maximum generality or something like that. It's just, if something can be generalized, then it should be. If something can be formulated in a more general sense, then that would be preferable to something that's defined in a much more restricted restricted sense. Okay, so before we start, just a warning: this video is not going to be necessarily easy to understand. This is not going to be a superficial treatment of Principia Mathematica. If you're familiar with some of my other videos on Principia Mathematica, you probably know that I take Principia Mathematica very seriously, and I go into quite a lot of detail. So there are going to be some prerequisites. I'm going to be explaining certain things as I go along, but I'm not necessarily going to be able to explain absolutely everything. So if you don't understand what I'm talking about in this video, it might be worth looking at some of my other videos where I go through some of the more elementary concepts of Principia Mathematica in more detail. To understand the contents of this video, you will have to be quite determined to understand Principia Mathematica on quite high level. Okay, so where are we going to start? We're going to start with that proposition. What do I mean by that proposition? I mean that proposition that everybody always refers to when they talk about Principia Mathematica. 54.43. Okay, so what does this proposition say? This proposition asserts that when alpha and beta are members of the class 1, that this implies that the proposition that the logical product of alpha and beta is equal to the null class is equivalent to the proposition that the logical sum of alpha and beta is a member of the class 2. Okay, so something that I mentioned in my previous video, I've probably mentioned in some of my other videos as well, is this notion of typical ambiguity. The symbols 1, lambda, 2, for example, these are excuse me, typically ambiguous symbols. So what do we mean by that? Well, in this system of Principia Mathematica, we have these things called types. There's an infinite, for all intents and purposes, an infinite number of types. No matter how many types we've generated, we can always generate more. Types don't overlap. They are either types are identical or different. Okay, there's no kind of overlap between types. But types are classes of objects. They're defined to be classes of objects, or the extensions. So the range of significance of propositional functions. Types are the ranges of significance of propositional functions, and a type will correspond to a certain grouping of propositional functions in a certain way. Okay, so to each type, we have a null class, for example. Okay, so the null class is usually denoted using this symbol lambda, or uppercase lambda. But if I just write lambda, there's no indication given as to which type this refers to. In fact, we can't really refer to particular types objectively, because there's no concept of absolute type. There's only a concept of relative type. So I can only, if I have an object that is of a particular type, X, then I can talk about the type of the null class lambda relative to the object, the type of the object X, for example, or any other. In a given context, I can potentially relate different symbols to each other. But if I just talk about lambda, I could be talking about the null class of any that corresponds to any type. So all of these null classes, the null class that corresponds to this type is a distinct entity to the null class that corresponds to that type, which in turn is distinct to that entity, which is the null class of this other third type. Okay. So in other words, there's an infinite number of null classes, but we use the same symbol to represent them. So there's no, I'm not suggesting that there's any psychological difference between these concepts of null class. It's the same kind of psychological concept corresponding to each of these types. It's really a logical distinction that is made. So understand that there isn't psychological distinctions, and logical distinctions are not forced to be the same thing. So there are ways that I can in certain contexts indicate if I want to fix lambda to a particular type, and we'll see this later in the video, I expect. I can fix lambda to a particular type in various ways. There's ways of supplementing this notation, so I might be able to say lambda sub x, which would indicate that lambda is a class which belongs to the same type as those classes whose members are the same type as x. I could have, for example, lambda uppercase x, which would be the null class that corresponds to that type, which are classes whose members are classes which in turn contain members of the same type as x. So it can sound quite complicated, and this is why we use symbols extensively to express these kinds of concepts. But also, I can fix the type of lambda in other ways. So if I know that alpha is a class, for example, I can talk about the null class corresponding to the same type as alpha by writing it in this slightly it seems to be a bit more pedantic, it seems to be quite a strange symbol to see. But this symbol, the logical product of the class lambda and alpha, would indicate this would only be significant. It could only be significant if lambda and alpha were classes of the same type. So this forces lambda to be of the same type as alpha. But if you look in chapter 24 or something like that, what you'll find is that this is equal to lambda. But by writing lambda as the logical product of lambda and alpha, I'm stressing that this null class that I'm talking about is of a particular type, and I'm relating it to the class alpha, the type that alpha belongs to. Okay, so what does this proposition 54.43 state, or in kind of intuitive plain English, I guess? Well, one is it's the class of unit classes of any given type. So just like lambda, there's an infinite number of ones corresponding to each type. And the members of the class 1, so it's a class of classes, and the members are unit classes. So classes that have a single member. Okay, so if we know that alpha and beta are members of the class 1, then alpha must be some unit class corresponding to some object x. In other words, alpha is that class whose only member is x, and beta is the unit class of some object y. If their logical product, the logical product of alpha and beta, is equal to the null class, that will imply that x is not equal to y. So x and y are distinct objects, terms, whatever you want to call them. So if I've got, alpha and beta must be of the same type here for reasons of significance. If I've got the logical product of alpha and beta and the logical sum of alpha and beta, this is only significant if alpha and beta are classes of the same type. So they must be classes and they must be of the same type. And this is all something that's always in the back of your mind when it comes to Principia Mathematica, potentially. And it's going to be something that is going to feature very heavily later in, particularly if you do progress onto volume 2, considerations about different types really does come to the fore. Okay, so if we've got two classes of the same type, but they're both unit classes, but the member of one is different from the member of the other, we find their logical sum, then what we end up with is the logical sum of alpha and beta. There are exactly two members to this class, which are x and y. So, since the logical sum of alpha and beta is a class with exactly two members, it is a member of the class defined as 2. 2 is defined to be the class of classes of a particular type which have exactly two members. The class of all classes of a particular type which have exactly two members. Okay? So, interestingly as well, we don't necessarily have the number 2. Just 2 is an ambiguous, it's a symbol that is ambiguous as to type, but there are some types potentially which do not have a class that we can call the number 2, or we can try, but it will turn out that potentially in the lowest class, so when we're talking about the class of individuals, as I've explained before, we can only prove that there is at least one individual. So worst case scenario, if there is only one individual, then in the lowest type, there is no, well, we can talk about the class 2, but unfortunately it would just be equal to the null class. 3 will be equal to, so 3 will be defined in a kind of analogous way. The class of all classes of a particular type that have exactly 3 members, for the class of all classes of a particular type that have exactly 4 members. And by the way, we don't need a notion of number. These don't presuppose the notion of number. So even though I'm talking about the class of all classes with exactly 3 members, we don't need to have a notion of 3 necessarily. In fact, we don't need a notion of 3 to form classes of 3 members with exactly 3 members and collect them all together. There are ways of doing this which are explained in detail in Principia Mathematica and in Principles of Mathematics as well, Russell's Principles of Mathematics. We can create what are called one-to-one correspondences between classes without presupposing any concept of number. Okay, so in this lowest type, if 2 is equal to the null class, 3 will also be equal to the null class, 4 will also be equal to the null class. So we have this problem with cardinal numbers in that potentially if we go to a particular type, the cardinal numbers may only make sense effectively up to a certain point. So let's assume that we understand what we mean by cardinal number, and we've got order and stuff like that defined on cardinal numbers. Okay, so we can, given a particular type, there might be a greatest cardinal number, and any cardinal number beyond that will just be effectively equal to the null class. This will typically be the case if we've got a finite number of individuals, and we go up through a finite number of types. We'll only ever have a finite number of cardinal numbers, so we need the axiom of infinity to. If we assume the axiom of infinity, then that will assume the existence of an infinite class somewhere in one of the types. I'll be saying a lot more about cardinal numbers, and because there's different types of cardinal numbers that we need to consider. It gets much more complicated in volume 2 than it was in volume 1. So we might think that we can just take something similar to what we see here in proposition 54.43 as kind of corresponding to addition. So here we took it a member of the class 1, 2 members of the class 1, 2 different members of the class 1, and kind of jammed them together to form a member of the class 2. So maybe what we could do is we could have gamma, which is a member of the class 2, and delta, which is a member of the class 3, and we can take these 2 classes, we can jam them together, and we get gamma logical sum of gamma and delta, and this will be a member of 5. And that we might see this as representing somehow 2 plus 3 is equal to 5. Now, I'm not saying that this doesn't work or that it can't work, but it's very limited. There's all sorts of restrictions that are going to have to be placed on this. First of all, gamma and delta are going to have to be classes of the same type for this to work. So that means that the 2 and the 3 that we're talking about here have to be of the same type. The 5 will have to be of the same type as the 2 and the 3. So this can only take place within a particular given type. But remember, one of the aims of Principia Mathematica is greater generality. So is it possible for us to, rather than just sticking to adding cardinal numbers of the same type, can we add cardinal numbers of different types? The answer to that is yes, we can. It's more complicated, naturally, but it does provide a much more general notion of addition of cardinal numbers, and it's that route that Whitehead and Russell have chosen to take. Okay, so interestingly, after proposition 54.43, there is a comment from this proposition. So this is a comment immediately following the demonstration of proposition 54.43. From this proposition, it will follow, when arithmetical addition has been defined, that 1 plus 1 equals 2. So we've got to be careful how we interpret this, because it is not at all an immediate consequence of proposition 54.43. There's a lot of stuff that's going to have to be put in place first before we can use this proposition to deduce that 1 plus 1 is going to be equal to 2. This proposition 54.43, I've gone through in another video in more detail. So what I did in that video is I took the demonstration that's given in Principia Mathematica and I've kind of expanded it, because as I've said in some of my other videos, a lot of the demonstrations at this point in Principia Mathematica are kind of sketch. So what I've done is I've expanded the demonstration, filled in some of the details that have been kind of skipped over, and gone through kind of line by line. So it's my own demonstration. Now, understands that if you have watched that video and you understand it, what you'll probably realize is that the demonstration that I've given in that video can actually be shortened without really losing any detail. There are okay, the reason for this was when I put that together, that video, we had a power cut and the power was off for 2 or 3 hours. So I didn't have anything else to do. So my laptop still had some battery. So I decided to put that video together. So I wrote out the demonstration, figured out the demonstration, put the video together. The next day when the power was back on, I recorded the video, and I didn't really check over in too much detail what I was putting in. I knew it was for all intents and purposes correct, but I realized actually after I'd recorded the video that there was some redundancy in the demonstration. So it's correct as far as I can see, but there is some redundancy. But if you do want to find out more about proposition 54.43, then refer to that video. And again, it's not a superficial, just quick glance at 54.43. It is an analysis of that particular proposition. Okay, so let's have a talk about how Whitehead and Russell define the concept of cardinal number in Principia Mathematica, because this is quite tricky. On the face of it, it seems to be quite straightforward, quite simple, but there are certain technical difficulties that you encounter with cardinal numbers in Principia Mathematica. The notation, unfortunately, has to be expanded. The basic notation that we would like to use for cardinal numbers is not, unfortunately, expressive enough. So we'll have a look at that in a second. So to get to the notion of cardinal number, we've got to go through the notion of similarity of classes. So two classes are similar, and we use this symbol to express similarity. The relation of similarity between two classes, alpha and beta, if there is a one-to-one correspondence between alpha and beta. So a one-to-one correspondence is, it's a relation which is simultaneously many-to-one relation and a one-to-many relation. But intuitively speaking, it means that if you've got two classes, alpha and beta, to every member of alpha has exactly one correlate in beta. So if this is alpha, this is beta. Each member of alpha has exactly one correlate in beta, and each member of beta has exactly one correlate in alpha. Okay, so we get this this one-to-one correspondence. So for all intents and purposes, alpha and beta have the same number of members, but we don't need a concept of number. We don't presuppose a concept of number in order to establish that there are an equal number of members in alpha and beta. Very importantly, alpha and beta do not have to be classes of the same type. This is a good thing, but it does bring with it some issues. Remember, greater generality, that's what we're after. So we don't really want to be restricting this relation SM to classes just of a particular type. Okay, SM, by the way, is a typically ambiguous symbol. Okay, but it can be used to compare the sizes of classes even from different types. So alpha and beta might be of different types. So what we can do is we can collect all of the classes. Let's say we take the class beta. We want to find all of the classes of a particular type that are similar to beta. How do we write this? Well, we can start by trying to write it like this. Cardinal number of beta, which is defined to be SM right arrow primed beta. So we've come across this notation, the right R right arrow in chapter 30 something, 31 or 32, something like that. So R right arrow is the class of terms. So I'll use R primed alpha is the class of terms, each of which has relation R to alpha. Okay, so SM right arrow primed beta is the class of terms, and notice it's a descriptive function because there is a unique class, such class. It's the class of terms, or the class of classes, which have the relation SM to beta. In other words, the class of classes which are similar to the class beta. And this is what we call the cardinal number of beta. This is not referring to a particular type, though. NC primed beta. How do we know which class of classes we're talking about if we can relate classes of any type, potentially, to beta? Via this relation SM, the notation gives no indication to me here which class of classes I'm talking about. Okay, and so relative to beta, we've got there is a cardinal number that corresponds to the cardinal number of beta that is kind of on the same level as beta. Above, in terms of type, I mean, higher type than beta or lower type than beta, potentially. Not always lower type, though. So how do I know where I am? How do I know if I'm on the same level as beta? Higher than beta? If I'm higher, how much higher? If I'm lower than beta, how much lower? So this is where the notation has to be expanded a little bit. And what we do, so this is if you start on volume 2, what you'll come across are homogeneous cardinals. There's ascending cardinals and descending cardinals. Okay, so if we've got beta here, and we've got all of these classes, so we've got alpha, we've got gamma, we've got delta, and these are all in NC primed beta over here. Okay, so all of these have relation SM to beta. So if alpha and beta are of the same, if alpha, gamma, delta, and so on are of the same type as beta, then the cardinal number that we're talking about here is a homogeneous cardinal. In fact, in that case, beta will also be in this class of classes. Okay, that's an important point which we'll need to refer to later on. On the other hand, if alpha, gamma, and delta are of a higher type than beta, we've got an ascending cardinal. This is not too much of a problem. Ascending cardinals they've got some nice properties. But if alpha, gamma, and delta are of a lower type than beta, we could potentially have difficulties. Okay. So I'm not going to go into too much detail on this, but what we're interested in ultimately is for the purposes of this video, we're interested in the homogeneous cardinal number corresponding to the class beta. So we write that in a particular way. So we write it as n sub 0 Mortal Kombat, n sub 0 c primed beta. I used to play that when I was a kid. Okay, so this would indicate that we're talking about here the cardinal number, the homogeneous cardinal number, effectively the one that is on the same level as beta, so to speak. We can go up to higher levels, so I'm not going to go into too much detail on this, but we can have, for example, n sub 1 c primed beta and n with a superscript of 1 c primed beta, and this will go down or up relative to beta. These are ascending and descending cardinals. I'm not sure if actually you'll be able to see that very well. Let me write it somewhere else on the screen. So n 0 c primed beta. That's what we're interested in. So remember this symbol because we're going to need it later. So this is what we mean by cardinal numbers. It's the class of classes of a particular type which are similar to a given class. And to ensure, and if we're wanting to the homogeneous cardinal number, then we denote it in this particular way. So it's the class of classes of the same type as beta, which are all similar to beta. So beta will be a member of that class. If it's a homogeneous cardinal, beta will be a member of that class. Okay, so let's move on. Let's have a look then at arithmetical class sums. Okay, arithmetical class sums. Before I start on this, I'm going to have to talk a little bit about this relation. Okay, x down arrow y. So this is called an ordinal couple. Okay, x down arrow y. And it's kind of an abbreviated notation for this, which is iota primed x up arrow iota primed y, which in turn, which is a special case of the more general case, which is alpha up arrow beta. Okay, so working from the more general case, let me just explain what this means then. So this relation, alpha up arrow beta, will hold between, no, better not use x and y actually, I'll use u and v. This will hold if and only if u is a member of the class alpha and v is a member of the class beta. So analogously then, if alpha is replaced with the unit class of X, in other words, the class whose only member is X, and beta is replaced with the class whose only member is Y, the unit class of Y, then this will hold if and only if U is a member of the unit class of X, in other words, if U is equal to X, and if V is equal to Y. X and Y do not have to be of the same type. Okay? Alpha and beta do not have to be classes of the same type. So therefore, the relation X down arrow Y will hold if and only if U equals X and V is equal to Y. Okay? Another important point, if X down arrow Y is equal to Z down arrow W, then this implies that X will be equal to Z. In fact, this is equivalent to X is equal to Z and Y is equal to W. Okay, this is proved in, so ordinal couples are defined in chapter 55. And which proposition is it? 55.202 shows that X down arrow Y equals Z down arrow W is equivalent to the proposition that X equals Z and Y equals W. These are relations. These down arrow, X down arrow Y, they're relations. And the down arrow is also a double descriptive function. So chapter 38, we're going to be using, I'm going to be not necessarily overtly, I'm not going to draw much attention to it, but that idea is is going to be coming into this shortly, very shortly actually. Okay, so once we've got this in place, then we can start to look at the arithmetical class sum. So we're into volume 2 now, so let me just change books. So we're into chapter 110 here. In fact, I don't need to open the book, I know it. So if alpha and beta are classes, we can define the arithmetical class sum. So this addition symbol here is not the addition symbol that we're maybe familiar with, you know, that we learned back when we were 4 or 5 years old, you know, when we first started school, for example. It's a different symbol. It's corresponding to a completely different thing. Okay. This is defined to be down arrow lambda, the logical product of lambda and beta, double primed iota, double primed alpha, logical sum lambda alpha down arrow double primed iota double primed beta. Okay, so this is the arithmetical class sum. Okay, what we're looking to do here is to, alpha and beta do not have to be classes of the same type. What we're wanting to do here is to take into consideration the number of terms in alpha, the number of terms in beta, and to form a new class which we can guarantee will have the same number of terms as alpha and beta, the number of terms of alpha and the number of terms of beta combined. But we can't just combine alpha and beta if they are of different types. We can't just find their logical sum. We can't just say, oh, well, alpha and beta are of the same type, but they're mutually exclusive, and just jam them together. That's not how it works, unfortunately, for the level of generality that Whitehead and Russell are aiming for. So this is, you might think, well, why make it so difficult? Whitehead and Russell don't do things because they're easy. They do things because they're hard. Okay, potentially, anyway. Right, so what's going on here? Let's have a breakdown of all of this notation. So let's start with this iota double primed alpha. So what is this? How can I start to understand, this is a class, by the way. How can I start to understand what is in this class? So this is the class of terms. What shall I use? X, such that x iota y holds for some y in the class alpha. Okay, so this is introduced in chapter 37. Right, well, what is iota? Iota is a fixed relation. This is introduced in section A of part 2. It's the relation of the unit class of a particular object to the object which is the only member of that unit class. Okay, so this relation x iota y will hold if and only if x is equal to the unit class of y. Okay, so iota double primed alpha is the class of terms, or the class of classes even. The class of classes iota primed y for each y is a member of alpha. Okay, so for each y in alpha, there is going to be there's going to be a unit class which corresponds to it. So iota double primed alpha will contain all of the unit classes. A unit class, one unit class corresponding to each y in alpha. So if you notice then, iota double primed alpha is going to be similar to alpha. I think that is probably proved somewhere in Principia Mathematica, but I would imagine in section 73 somewhere. But intuitively, you can see you don't need Principia Mathematica, the formal demonstration of Principia Mathematica to tell you that. Okay, so what about this then? So we've got that settled. What about down arrow lambda logical product beta double primed iota double primed alpha? Okay, so remember that the relation down arrow, let me say down arrow x, this is the relation of y down arrow x to y for any object y. Okay, so this is chapter 38, double descriptive function. So this down arrow lambda logical product beta, this is a relation which is derived from a double descriptive function. Okay, so y down arrow x is going to be a relation. Okay, so we've got the class of terms of the form z down arrow lambda beta, where z is going to be a member of iota double primed alpha. Okay, so this is how I've explained this in a previous video. This is how I kind of start to build a picture. So I don't look at this symbol, down arrow, lambda, logical product beta, double primed iota, double primed alpha, and just immediately know what's in that class. I don't know. I've got to go through step by step. But I've personally got a systematic way. Some people might think, well, it's a very long-winded way of going about it, but the thing is, it works for me. I can consistently use whatever systematic way I have of figuring out what's in this class. I can use it to consistently get to build a decent enough picture. Okay, so we've got, in other words, a class of relations of the form. So now I've got the information there in front of me. Of the form, well, if z is a member of iota double primed alpha, then z must be of the form iota primed y. Okay, so we've got a class of relations of the form iota primed y, down arrow, logical product of lambda and beta, where y is a member of alpha. Okay, so in other words, this here is a class of relations. Now we've got this weird symbol going on here, this lambda logical product beta. Remember what I was saying earlier? This is a way to fix the type of the lambda. If we just had lambda there, which lambda are we talking about? Here, lambda logical product beta forces that lambda to be of the same type as beta. So even though we're using the same symbol, lambda, in the logical products with beta and the logical products with alpha, they're talking about different lambdas. They're talking about different null classes. Really, it's probably better to think about, rather than just lambda here, to see this lambda logical products beta as being like a single symbol representing the null class corresponding to that particular type that beta belongs to. Okay. So I'm not going to go through it step by step again. Oh, what's happened there? But analogously, we get that the logical product of lambda and alpha, down arrow, double primed, iota, double primed, beta. This is the class of terms class of relations, actually. I can be more specific. Class of relations of the form lambda, alpha, down arrow, iota, primed, w, where w is a member of beta. So this is completely analogously to what we had. Okay, so on the one hand, then we've got this class of relations, iota primed y, down arrow, lambda, beta, where y is a member of the class alpha. And on the other hand, we've got this class of relations alpha, down arrow, iota prime w, where w is a member of beta. So what I need really is that these relations are relations of the same type. So then the classes which they form are of the same type, and therefore I can find their logical sum. Okay, because if we go back to this, we've got the logical sum symbol here. For this to be significant, it demands that the class, the two classes that we're trying to find the logical sum of, must be compatible. That is, of the same type. The type of a class is determined by the type of its members. So if I can show that the members of each of these classes are of the same type, then the classes themselves are of the same type. So, okay, y is a member of alpha. So that means that any class that contains y as a member must be of the same type as alpha. In particular, the unit class y, the unit class of y, sorry, is going to be of the same type as alpha. So that's the same type as alpha. Lambda logical product alpha, as we've already seen, that forces this lambda to be of the same type as alpha. It's a null class, but it's of the same type as alpha. So we've got agreement there with these relations. On the other hand, we've got w is a member of beta, so iota primes w, the unit class of w, must be the same type as beta. And the logical product of lambda and beta forces this to be the null class corresponding to beta. So we've got agreement there. So what we find is that the relations in each of these individual classes are of the same type. Okay, a class can only ever have members of a single type. So each of these classes has members of the same type as the other one. So the classes themselves must be of the same type, and therefore I can find their logical sum. Everything's falling into place. That's good. So what I can do then is I can jam all of these relations together into this class alpha plus beta. Okay, so the number of relations. So okay, when will this relation iota primed y down arrow lambda beta, when will this hold? This will hold only in the case, so if I've got u v, this will hold only in the case when u is equal to iota primed y and v is equal to lambda in lambda, logical products of lambda and beta. Well, v, there's only one thing that v can be then, right? We're not saying that v is a member of the null class. We're saying here that v is the null class. Okay, but there is only one null class, so v can only be one thing. There's only one term that v can be. On the other hand, u can, it ranges. It can be each of these unit classes. But remember, this class of unit classes that we formed, this iota double primed alpha, is of the same size as alpha. For each member of alpha, there is a unit class that corresponds to it, and for each unit class in iota double primed alpha, there is a member of alpha that corresponds to it. They're the same size. They're similar. So in other words, the number of relations of the form iota primed y down arrow logical products of lambda and beta, there's exactly as many relations of that form as there are members of the class alpha. Similarly, relations of the form lambda logical product alpha down arrow iota primed w, there's exactly the number of relations of this form is exactly the same as the number of terms in the class beta. So this class that we're forming from these two types of relation, how many relations are going to be there? It's the same number of terms as the number of terms of alpha and the number of terms of beta combined. So I'm not talking about alpha and beta being combined. I'm talking about the number of terms of alpha and the number of terms of beta being combined. Okay, so this class that we end up with is that class that we write as alpha plus beta. Okay, so alpha plus beta is it's a class of terms, all of the same type naturally, but it's a new class. It's alpha plus beta is not a class of the same type as alpha or beta. It's related to the types of alpha and beta, but it's determined by the types of alpha and beta, but it's not of the same type as alpha and beta. Okay. So once we've got that in place, where next? Well, now we get onto the arithmetical sum of two cardinals. And okay, so let's say we've got the cardinal numbers mu and nu. Now, we don't want to use this plus symbol here because we're talking about a different type of addition now. We're talking about cardinal addition, so we put a little c down here. So plus sub c nu. And this is defined to be the class of, I can never remember, is this psi or something like that? I'm going to say psi. Anybody that knows the Greek alphabet better than I do, please let me know. Please correct me if I'm wrong. So this is there exists alpha and beta classes, alpha and beta, such that mu is equal to n sub 0 Mortal Kombat C primed alpha, nu is equal to n sub 0 C primed beta, and psi is similar to the arithmetical class sum of alpha and beta. So this is how we define the sum of two cardinal numbers. So it's useful for mu to be defined as the homogeneous cardinal number of alpha, because in that case alpha will be a member of mu. In other words, all we're doing here really is just we're looking at mu, this cardinal number, and we're just taking one of the classes out and just saying, okay, that's alpha. Similarly for nu, we've got nu. Beta, the betas that we're after will be in there. They're all, because it's a homogeneous cardinal. So beta, we can just choose whichever one we want. Now, importantly, this definition doesn't actually require mu and nu to be cardinal numbers. It's just that if mu and nu are not cardinal numbers, then mu plus sub c nu will just be equal to the null class. Okay, there will be no classes that satisfy this. So again, greatest level of generality. We're not defining strictly addition of cardinal numbers here. We're defining a particular type of operation between classes of any sort. It's just it works when it's interesting. It is when the two classes that we have are cardinal numbers. Okay, so it's not limited to cardinal numbers, strictly speaking, and the cardinal numbers do not have to be of the same type. Mu and nu do not have to be of the same type, so therefore alpha and beta will not necessarily be of the same type. So we see here the alpha plus beta, that's the arithmetical class sum that we've just talked about. So we're finding all of the xi's of a particular type that are similar to this arithmetical class sum. Okay. So from this, it naturally follows that 1 plus 1 is equal to 2. Notice in here, in this, if we didn't require mu and nu to be cardinal numbers of the same type, we don't require the ones, this one and this one to be of the same type either. Okay. So how does this work? What do we do? Well, we've got the cardinal number 1. Let's take the first one. So this is our mu for all intents and purposes. We look in there, we choose one of the unit classes. Okay, that's going to become our alpha. Okay, so alpha will be some unit class corresponding to, I don't know, x. And then we look at the other one and we choose a unit class. X and Y might be of different types. Okay, they may also be the same unit class. There's no guarantee. If mu and nu are of the same type, in other words, if this one and this one are the same one, there's no saying that what happens if we choose the same unit class for alpha and beta. Doesn't make a difference. We can do that. Again, greatest level of generality. It's brilliant. So what is alpha and alpha plus beta going to be? This is where proposition 54.43 really comes in. Okay, because we're going to get these two classes. I'll go on to another page. So we're going to get down arrow, what was it? Beta double primed iota alpha whatever on the one hand, and lambda alpha down arrow double primed iota double primed beta. So I'm just using the notation from the definition here, but this class will end up being effectively iota primed, so it's a member of alpha. It's just going to be x, sorry. Is it? Yeah, well, either way, this class is going to contain a single relation. I've not thought about it enough, to be honest with you right now, but it's this. There's going to be one relation in here, and there's going to be one relation in here. Okay, so when we put them together, 50, and they're going to be unit classes, by the way. If there's one relation, if this class has one member, it's a unit class. So it's the unit class of something. This is going to be a unit class. They're going to be unit classes of the same type, which is exactly 54.43. Unit classes of the same type. Unit classes are both members of one of a certain type. We've seen that they have no common members. So this class and this class have no common members. So therefore their logical product is equal to the null class. Their logical sum is going to be a member of the class 2. Okay, so alpha plus beta is going to be a member of the class 2 of a particular type. So then going back to our definition of cardinal addition, we're looking for all those psi of a particular type, which are similar to alpha plus beta, which is a member of the class 2. Okay, and it follows that 1 plus 1 is equal to 2. But, final few comments, the 2 that we end up with is not necessarily of the same type as the ones that we started with. The ones that we started with are not necessarily, respectively, of the same type. So we've got types flying around all over the place here, different types. But it's just, I mean, it's incredible that Whitehead and Russell actually managed to figure all of this stuff out. I would have given up a long time ago with all of this stuff. But Whitehead and Russell managed to actually figure this out in this level of generality. Okay, so when we're talking about showing in Principia Mathematica that 1 plus 1 equals 2, we're not talking about one finger, 2 finger. We're talking about something that is much. The structure of these entities is very, very complicated. So this proposition that 1 plus 1 equals 2, which is a proposition 110 point, what is it? 110.643. The amount of work that has had to actually go into that is absolutely immense. There are some other propositions, 110.64, which is 0 plus 0 is equal to 0, 110.641, 1 plus 0 equals 0 plus 1 equals 1, and so on and so forth. So all of these are just bits of evidence, really fragments of evidence that the system that Whitehead and Russell that they're developing is at least behaving in a way that we kind of need it to. Okay, so yes, the system of Principia Mathematica is deeply flawed. It didn't live up to the author's expectations. It doesn't do what it's supposed to do ultimately, but nevertheless, at least it behaves in something resembling the kind of way that we expect it and want it to behave, at least on this level. Okay, so I think that's just about it for this video. I think I've said about everything that I want to say. If you do have any questions about anything that I've said in this video, then please feel free to ask. I'm always open to questions. I'm probably going to keep doing my videos like this from now on, for the simple reason that I can get through stuff quicker. It does come with the downside that I'm probably a bit repetitive, a bit all over the place with my videos, but if there is something that's genuinely interesting in my videos, then if you're interested enough and patient enough to find it, then hopefully you will come across something that you find useful. I'll try to put in the description to the video kind of a summary without going into too much detail about what's entailed in this video. Also in the description to this video, I will leave a link to my Buy Me a Coffee page. As you can see, I like coffee. If you are in a position to make a small donation, that will be gratefully received. Please don't worry though, if you're not in a position to make any sort of donation, don't worry about it. Also, if you don't think my videos are worth making a donation for, then obviously don't make a donation. But thank you for watching. I hope you do find something useful in this video. And I don't know what I'm going to do in my next video. I've got lots of ideas. It's not necessarily just Principia Mathematica. I've got some Euler that I want to look at. I want to have a look at some Frege at some point. What else have I got? Quine, maybe. Veil. Who knows what I'll do next? I'm just looking at the books in my bookcase. I've got loads of stuff that I want to cover, and these videos, doing them like this now, gives me a bit more freedom. It allows me to make videos at a much faster rate. So thank you for watching, and I will look forward to seeing you in the next video.